Close your eyes for just a moment. Not to sleep, not yet, but to feel the gentle pulse of something extraordinary happening right now, in this very second, as you listen to these words. There, in the quiet darkness behind your eyelids, entire galaxies are firing. Constellations of electricity dance across a landscape more complex than any universe we've ever mapped. Rivers of chemical messages flow through canyons carved from billions of years of evolution. And all of it, every spark, every whisper, every silent symphony, is happening inside the 3 pounds of soft tissue cradled in your skull. Welcome back to the Midnight Explorer, where we wander through the gentle mysteries of our world, one story at a time. I'm here with you tonight, and together we're going to embark on perhaps our most intimate journey yet, into the silent universe inside us all. The human brain. 3 simple words that contain multitudes, 3 words that describe the most complex structure we know of in the entire cosmos, 3 words that somehow, incredibly, are capable of understanding themselves. Tonight, we won't rush. We won't hurry through facts and figures like students cramming for an exam. No, tonight we'll drift slowly through the chambers of this magnificent organ, the way you might walk through a cathedral at dusk, when the light slants golden through ancient windows, and every shadow holds a story. We'll trace the long, winding path of how we came to understand this mysterious universe within. We'll meet the curious souls who dared to peek inside the human skull, who mapped the unmappable, who asked questions that seemed impossible to answer. We'll discover how a wrinkled mass of tissue no bigger than a cantaloupe somehow creates every thought you've ever had, every dream you've dreamed, every moment of love and fear and wonder. So settle in. Pull your blanket a little closer. Let the world outside fade to a gentle murmur. The story we're about to tell begins not in a laboratory, but in the sands of ancient Egypt, where the first humans to truly wonder about the brain made a decision that would echo through millennia. And it begins, like so many great stories do, with a mystery. In the Valley of the Kings, on a desert afternoon 4,000 years ago, the sun hangs low and copper-bright over the limestone cliffs. Inside a tomb carved deep into the rock, priests move with practiced precision through the sacred ritual of mummification. The pharaoh has died, and his body must be prepared for the eternal journey ahead. These priests know the importance of every organ. The heart, precious heart, will be weighed against the feather of Ma'at in the underworld. It must be preserved with utmost care, placed in its own sacred canopic jar. The liver, the lungs, the stomach, each has its purpose in the afterlife. Each must be treated with reverence. But then there is the brain. Watch as the priest takes a long, hooked instrument, bronze, polished to a dull shine, and carefully inserts it through the nose. With practiced efficiency, he breaks through the thin bone at the top of the nasal cavity. The hook disappears into the skull. A few deft movements, and he begins to withdraw it, bringing with it small, liquefied pieces of gray-pink tissue. The brain, reduced to fragments, is discarded. Thrown away, like waste. The Egyptians, for all their wisdom, for all their sophisticated understanding of the body and the afterlife, believed the brain was merely stuffing, biological packing material that filled the skull with no more significance than straw. The heart, they were certain, was the seat of intelligence, of emotion, of the soul itself. They weren't alone in this belief. For thousands of years, humanity looked at the brain and saw nothing special. It was the heart that leapt when you were frightened, the heart that raced when you were in love, the heart that you could feel pounding in your chest during moments of passion or terror. The brain? The brain just sat there, silent and still, seemingly doing nothing at all. How strange it is to think about that the very organ allowing the Egyptians to think these thoughts, to develop their elaborate theology, to create their magnificent civilization, was the very organ they deemed worthless. The first glimmers of understanding. But not everyone discarded the brain so easily. Travel with me now from the desert sands of Egypt to the sun-drenched islands of ancient Greece to around 400 BCE. Here, on the island of Kos, a physician named Hippocrates, a man whose name would become synonymous with medicine itself, made a radical observation. He had treated many wounded soldiers, many injured athletes. He had seen what happened when a man took a blow to the head. And he noticed something that others had overlooked. When the brain was injured, the body suffered. Not just near the wound, but far from it. A blow to the left side of the head might paralyze the right side of the body. Damage to a specific area might steal away speech, or memory, or even personality. In his writings, Hippocrates made a statement that would have seemed revolutionary, perhaps even heretical to his contemporaries. Men ought to know that from the brain, and from the brain only, arise our pleasures, joys, laughter, and jests, as well as our sorrows, pains, griefs, and tears. Read those words again, slowly. Let them sink in. From the brain, and from the brain only. Not the heart, not the liver, not some mystical soul floating untethered in the body. The brain. But Hippocrates was ahead of his time. His insight, as brilliant as it was, would be largely forgotten, buried under centuries of competing theories and deeply held beliefs about the heart as the center of human existence. Aristotle's error. Only a few decades after Hippocrates, another Greek thinker, perhaps the most influential philosopher of all time, would set the field back centuries. Aristotle was a genius. His mind ranged across every field of knowledge: biology, physics, ethics, politics, poetry. He established the systematic study of logic. He laid the groundwork for the scientific method. He was, by any measure, one of the greatest thinkers humanity has ever produced. And he was completely wrong about the brain. Aristotle believed the heart was the seat of intelligence, sensation, and emotion. The brain, in his view, was merely a radiator, a cooling system for the blood. He thought it was a mass of cold, insensitive tissue whose only purpose was to balance out the heat generated by the passionate, intelligent heart. It's easy, from our modern vantage point, to smile at this error. But pause for a moment and consider. Aristotle was working with only his observations and his reason. When he touched a brain, removed from a body, no longer pulsing with life, it was cold and seemingly inert. The heart, by contrast, beat with obvious vitality. Blood coursed through it, warm and alive. Given what he could observe with his own senses, Aristotle's conclusion wasn't foolish, it was logical. And because it was Aristotle who said it, Aristotle, whose works would become the foundation of Western thought for 2,000 years, his error became doctrine. For centuries upon centuries, the greatest minds in Europe accepted without question that the heart was the seat of thought, and the brain was merely a cooling organ. But not everyone in the ancient world agreed. Let's move forward now to the 2nd century CE, to the bustling city of Rome at the height of its power. Here, a Greek physician named Galen served as doctor to the gladiators, a position that gave him unique, if tragic, opportunities to study anatomy. Imagine Galen after the games working by lamplight in the physician's quarters beneath the Colosseum. Before him lies the body of a gladiator who fell that afternoon. The crowd has gone home. The sand has been raked clean. But here, in the quiet, Galen has a chance to observe what few physicians ever see: the fresh interior of the human body. Galen couldn't legally dissect human bodies. Roman law forbade it. But the gladiators who died in the arena and the criminals who were executed, these gave him glimpses into human anatomy. He supplemented this knowledge with careful dissections of animals, pigs, monkeys, even elephants. And through his observations, Galen came to a conclusion that contradicted Aristotle himself. The brain, Galen argued, was the center of the nervous system. He had traced the nerves, those pale, thread-like structures that branched throughout the body, and found that they all led back to the brain and spinal cord. He had seen what happened when nerves were cut. The parts of the body they served lost sensation and movement. More than this, Galen identified different parts of the brain and speculated on their functions. He was the first.
Now we understood the brain's basic architecture. Billions of neurons, organized into different regions, communicating across synapses. But how did they communicate? What was the actual mechanism? The answer, when it finally emerged in the early 20th century, was both simpler and more complex than anyone had imagined. Imagine a single neuron, if you will. Picture it like a tree, with branches reaching out to receive signals and a long trunk reaching away to send signals onward. This neuron sits quietly, maintaining an electrical charge across its membrane, negative on the inside, positive on the outside. It's like a tiny battery, constantly charged and ready. When signals from other neurons reach our neuron's branches, its dendrites, something remarkable happens. If enough signals arrive, if enough of the neighboring neurons are telling this neuron to fire, the electrical charge suddenly reverses. It happens in a cascade, starting at the cell body and racing down the axon, the long trunk of the neuron, at speeds up to 250 miles per hour. This is the action potential, the fundamental unit of information in the brain. When the electrical signal reaches the end of the axon, it triggers the release of chemicals, neurotransmitters, into the synaptic gap. These chemicals drift across the tiny space between neurons and bind to receptors on the next neuron, passing the message along. Then the neuron resets, pumping ions back across its membrane, restoring the charge, getting ready to fire again. The whole process takes a few milliseconds. This is happening in your brain right now as you listen to these words. Not in one neuron, but in billions simultaneously. Vast networks of neurons firing in patterns, passing messages back and forth in an electrical and chemical symphony of incomprehensible complexity. The neurotransmitter revolution. The discovery of neurotransmitters, those chemical messengers that carry signals across synapses, opened up an entirely new understanding of how the brain works. It started in 1921 with Otto Lowy, a German pharmacologist who had a dream, literally a dream about an experiment. He woke in the middle of the night, scribbled down his idea, and went back to sleep. In the morning, he couldn't read his own handwriting. But the next night, the dream returned. This time, he went straight to his laboratory in the middle of the night and performed the experiment. Lowy took 2 frog hearts, both still beating in dishes of saline solution. He stimulated the nerve of one heart and collected the fluid surrounding it. When he transferred this fluid to the second heart, its beat slowed, just as if its nerve had been stimulated. The nerve, Lowy realized, must have released a chemical into the fluid, a chemical that carried its signal. He called this substance Vagestoff. We now know it as acetylcholine, the first neurotransmitter to be identified. Over the following decades, dozens more neurotransmitters would be discovered, each with its own role in the brain's vast signaling network. Dopamine, the molecule of motivation and reward, the chemical rush that makes us feel good when we accomplish something or anticipate something pleasurable. Serotonin, the mood stabilizer, the neurotransmitter that seems to keep our emotional state on an even keel. GABA, gamma-aminobutyric acid, the brain's main inhibitory neurotransmitter, the one that tells neurons to calm down, to stop firing, to quiet the noise. Glutamate, the opposite, the main excitatory neurotransmitter, the one that revs neurons up and gets them firing. And many, many others, each contributing to the brain's staggeringly complex chemical environment. Understanding neurotransmitters suddenly made sense of so many things. Depression, we learned, might involve imbalances in serotonin or dopamine. Parkinson's disease resulted from the death of dopamine-producing neurons in a specific part of the brain. Schizophrenia seemed to involve excessive dopamine activity in certain brain regions. Drugs, both medicinal and recreational, worked by interfering with neurotransmitter systems. Prozac blocks the reuptake of serotonin, leaving more of it available in synapses. Morphine mimics endorphins, the brain's natural pain-killing chemicals. Cocaine blocks the reuptake of dopamine, flooding the brain with this pleasure-inducing chemical. The brain, we were learning, was not just electrical, but chemical. A vast pharmacy producing substances that could alter consciousness, mood, perception, everything that makes us human. Reading the brain's signals. By the 1920s, scientists could observe individual neurons firing. They could identify neurotransmitters. But what about the larger patterns? Could we observe the whole brain at work? The answer came from a German psychiatrist named Hans Berger. In 1924, Berger attached electrodes to a patient's scalp and connected them to a sensitive recording device. What he saw astonished him. Regular, rhythmic electrical waves emanating from the brain, visible even through the skull and scalp. He called it an electroencephalogram, an EEG, a recording of the brain's electrical activity. For the first time, we could see the brain thinking. Not in detail. An EEG is more like listening to a symphony from outside the concert hall. You can hear the general rises and falls, but not individual instruments. But we could see patterns. When people closed their eyes and relaxed, the EEG showed large, slow alpha waves, about 10 cycles per second. When they opened their eyes or focused on a task, faster beta waves appeared. During deep sleep, the waves became even slower and larger, delta waves rolling through the brain like slow ocean swells. Doctors soon discovered that EEGs could diagnose epilepsy, detect brain death, and provide insights into sleep disorders. Researchers used them to map out the different stages of sleep and to understand what the brain was doing during different mental states. But EEGs had limitations. They could show overall patterns, but not which specific parts of the brain were active. For that, we needed new technologies. Windows into the living brain. The next revolution came with brain imaging. Technologies that could take pictures of the living brain, showing not just structure, but function. The first of these was the CT scan, computed tomography, developed in the 1970s. It used X-rays to create detailed three-dimensional images of the brain's structure. Doctors could finally see tumors, strokes, and injuries inside the living brain without having to open the skull. But CT scans only showed structure, not activity. That changed with PET scans, positron emission tomography, which could show which parts of the brain were using the most energy, and therefore presumably most active during different tasks. And then came fMRI, functional magnetic resonance imaging, arguably the most important tool in modern neuroscience. fMRI detects changes in blood flow in the brain. Active neurons need more oxygen, so blood flow increases to active areas. An fMRI can detect these changes in real time, creating a moving picture of brain activity. Imagine lying in an fMRI machine, listening to music you love. The scanner can show researchers which parts of your brain light up: auditory cortex processing the sound, motor areas responding to the rhythm, limbic regions flooding with emotion, memory systems retrieving associations with that song. Or imagine reading a sentence, any sentence, even this one. The fMRI would show activity in visual cortex as your eyes track the words, Wernicke's area as you process the language, frontal regions as you extract meaning, and a constellation of other areas retrieving memories and knowledge that give context to what you're reading. For the first time in history, we could watch thoughts happen. We could see that when someone looks at a face, a specific region in the temporal lobe, the fusiform face area, becomes active. When someone navigates through space, the hippocampus lights up. When someone feels pain, a network of regions, including the insula and anterior cingulate cortex, responds. We could map not just where these functions occurred, but how different brain regions worked together, forming networks and systems. The brain, we were learning, was not just a collection of independent modules, but an integrated whole.
Let's step now into a cold workshop in Florence, around the year 1490. It's late at night, perhaps 2 or 3 in the morning. A single lantern casts flickering light across a wooden table where Leonardo da Vinci works in secret, in silence, his brush moving across parchment with the same precision he brings to his paintings. But he's not painting tonight. Tonight, he's drawing what he sees before him, the dissected head of a criminal, obtained through connections that history hasn't fully recorded, open to reveal the brain within. Leonardo approached the brain the way he approached everything, with insatiable curiosity and an artist's eye for detail. He drew what he saw with unprecedented accuracy: the convolutions of the brain's surface, the ventricles inside, the nerves extending downward. In his notebooks, written in his characteristic mirror script, perhaps to keep his observations private, Leonardo sketched and theorized. He, like Galen before him, believed the ventricles were crucial to thought and sensation. He drew them carefully, trying to understand their shape and position. But Leonardo was working in secret, in violation of laws both civil and religious. His notebooks were private, not published. His insights, brilliant as they were, remained largely hidden until centuries after his death. He was not alone in this clandestine pursuit. Vesalius and birth of modern anatomy. The true revolution in brain science would come a few decades later with a young Belgian anatomist named Andreas Vesalius. Imagine Vesalius in Padua, Italy in 1540. He's barely 30 years old, but he's already gained a reputation for his theatrical public dissections. Unlike the typical anatomy lessons of his time, where a professor read from Galen while a barber surgeon did the actual cutting, often on an animal body, Vesalius insisted on doing the dissection himself on human cadavers, while students crowded around to see. This was radical. This was almost unthinkable. But Vesalius had noticed something that troubled him deeply. Galen's descriptions didn't always match what he saw when he opened human bodies. And no wonder, Galen had worked primarily with animals. Some of his descriptions were of monkey anatomy, not human anatomy. For 14 centuries, no one had questioned this. Galen was authority. If your observations didn't match Galen's descriptions, it was assumed you were observing incorrectly, not that Galen might be wrong. Vesalius dared to question.
In 1543, the same year Copernicus published his theory that the Earth revolves around the Sun, Vesalius published De Humani Corporis Fabrica, on the fabric of the human body. It was a masterpiece of medical illustration and anatomical description, including detailed engravings of the brain. The drawings in Vesalius's work are beautiful even today, eerily beautiful perhaps. Corpses posed like living figures in Renaissance landscapes, their bodies opened to show the structures within. Skulls tilted back to reveal the brain, illustrated with an accuracy that had never been achieved before. Vesalius described the structure of the brain with unprecedented detail. He showed that humans, like other animals, had similar brain structures. He questioned the old theory that the ventricles were the seat of thought. They were just empty spaces filled with fluid after all. But even Vesalius, revolutionary as he was, couldn't fully explain what the brain actually did. He could describe its shape, its parts, its structure, but function? Function remained a mystery, wrapped in that gray, convoluted tissue. The age of observation. Still, the door was now open. Anatomy had become a legitimate field of study. Medical schools across Europe began conducting regular dissections. Artists studied anatomy to make their paintings more realistic. The human body, including the brain, was no longer forbidden territory. In the decades and centuries that followed, dozens of anatomists would contribute pieces to the puzzle. Thomas Willis, an English physician working in the 1660s, produced the most detailed description of the brain yet created. He coined the term neurology. He described the circle of arteries at the base of the brain that still bears his name, the circle of Willis. He was one of the first to seriously suggest that different parts of the brain might have different functions. Picture Willis in his study at Oxford, surrounded by the brains he had carefully preserved in wine and vinegar. By candlelight, he would make meticulous drawings, trying to understand the purpose of each fold and structure. He noticed that the cerebral cortex, the wrinkled outer layer of the brain, was much larger in humans than in other animals. Could this be, he wondered, the seat of human intelligence, the thing that made us different from beasts? It was a reasonable guess, and like Hippocrates' insight 2,000 years earlier, it was correct. But Willis couldn't prove it. He could only observe and speculate. The electrical discovery. Let's travel to Bologna, Italy in 1780. In a laboratory at the university, Luigi Galvani, a physician and physicist, is conducting experiments with electricity, the mysterious force that had captivated natural philosophers for decades. Galvani had dissected a frog and hung its legs on a copper hook. When the legs touched an iron railing, something extraordinary happened. They twitched. They moved as if alive, though the frog was long dead. Galvani repeated the experiment again and again. Each time, when two different metals completed a circuit with the frog's legs, the muscles contracted. He called it animal electricity. He believed he had discovered a special force, an electrical fluid that animated living tissue different from the electricity generated by machines. He was both right and wrong. There was no special animal electricity. The twitching was caused by ordinary electrical current generated by the interaction of the metals. But Galvani was right that electricity played a role in how muscles and nerves worked. This was a revelation that would echo through the next century. If nerves used electricity, then the brain, the organ where all nerves originated, must somehow generate and control electrical signals. The brain wasn't animated by mystical animal spirits, as Galen had thought. It was an electrical organ. Mapping the skull. As the 19th century dawned, the mystery of the brain had taken on new urgency. Scientists now knew the brain was central to human thought and behavior. They knew it was somehow electrical,
but they still didn't understand how it worked or why different people had such different mental abilities and personality traits. Into this fertile ground of curiosity stepped a Viennese physician named Franz Josef Gall, with a theory that would captivate the public imagination and ultimately lead science down a productive path despite being fundamentally wrong. Gall developed a theory called phrenology. The idea was this: different parts of the brain, Gall argued, controlled different mental faculties. Areas for combativeness, for amativeness, for hope, for caution, for each specific human trait. And because these areas of the brain grew with use, they would create bumps on the skull. By feeling the bumps on someone's head, a trained phrenologist could read their personality. It was nonsense, complete and utter nonsense. But buried in this nonsense was a seed of truth that would eventually flower into legitimate neuroscience. Gall was right that different parts of the brain had different functions. He was right that the brain's structure related to mental abilities. He was just completely wrong about being able to detect this by feeling someone's skull, and wrong about having such precise tiny areas for qualities like hope or caution. Phrenology became a sensation. In parlors across Europe and America, people had their heads examined by phrenologists who claimed to reveal their innermost nature through the bumps on their skulls. It was part science, part entertainment, part fortune-telling. And while the specifics were wrong, phrenology did something important. It made people think about the brain as a complex organ with different parts doing different things. It popularized neuroscience, even if it was bad neuroscience. The localization debate. The real breakthrough came in 1861 in Paris, where a physician named Paul Broca was about to make a discovery that would change neuroscience forever. Broca had a patient, a man who had lost the ability to speak. He could understand language perfectly well, his intelligence seemed intact, but when he tried to talk, only one syllable would emerge from his lips: ton. They called him Ton because it was the only sound he could make. When Ton died, Broca performed an autopsy and examined his brain. There, in the left frontal lobe, was a specific area of damage, a lesion caused by some long-ago injury or stroke. Broca theorized that this specific area, now called Broca's area, was responsible for speech production. Now that we understand the basic mechanics, neurons, synapses, neurotransmitters, electrical signals, let's step back and look at the larger architecture. How is this magnificent organ organized? The human brain is, in a sense, a history book. As you look at its different structures, you're looking at different chapters in our evolutionary story. At the very back, where the brain meets the spinal cord, sits the brain stem, the most ancient part of our brain, the part we share with reptiles and fish. This is the brain of survival, the brain of basic functions that keep us alive without our conscious thought. The brainstem controls your heartbeat. It regulates your breathing. It maintains your blood pressure and body temperature. It controls the sleep-wake cycle. Even if every higher brain region were damaged, the brainstem could keep your body alive. This is the part of the brain that was working even before you were born, keeping your tiny fetal heart beating, coordinating the primitive movements in the womb. Perched on top of the brainstem, like a smaller brain tucked underneath the larger one, sits the cerebellum, the little brain. Despite its small size, it contains more neurons than all the rest of the brain combined. The cerebellum is the master of movement. It coordinates every motion your body makes, every graceful gesture, every practiced skill. When you learn to play an instrument, to dance, to type without looking at your keyboard, that's your cerebellum building neural networks that turn conscious effort into automatic grace. But the cerebellum does more than coordinate movement. We're discovering that it also plays a role in language, attention, and emotional regulation. It's connected to almost every part of the brain, suggesting functions we're only beginning to understand. The emotional brain. Wrapped around the brainstem like a collar sits a collection of structures collectively called the limbic system, the emotional brain. Here we find the amygdala, two almond-shaped structures that process fear and other emotions. When you encounter something frightening, your amygdala responds in milliseconds, faster than conscious thought, triggering the fight or flight response before you even know you're afraid. The amygdala is why you can jump away from a snake before you consciously recognize it's a snake. It's our early warning system, tuned by millions of years of evolution to detect danger and respond instantly. But the amygdala isn't just about fear. It's involved in processing all emotionally significant events: joy, anger, sadness, disgust. It tags memories with emotional significance, which is why you remember emotionally charged events more vividly than mundane ones. Think of your most powerful memories: your first kiss, a moment of sudden loss, a triumph you'd worked toward for years. The reason these memories remain so vivid, so clear even decades later, is because your amygdala marked them as important, flooding them with neurochemicals that strengthen their encoding. Nearby sits the hippocampus, shaped like a seahorse, which is what hippocampus means in Greek. This structure is essential for forming new memories, for taking the swirling chaos of experience and consolidating it into lasting memory traces. A patient known as HM taught us this in one of neuroscience's most famous cases. In 1953, to treat severe epilepsy, surgeons removed HM's hippocampus on both sides. The seizure stopped, but HM lost the ability to form new long-term memories. He could remember his childhood, his life before the surgery, but after, nothing stuck. Every person he met was new each time. Every conversation started fresh. HM lived in an internal present, unable to encode new experiences into lasting memory. His case showed that memory isn't just one thing. It's a process, and the hippocampus is the gateway through which new memories must pass to become permanent. The hippocampus is also where we form our mental maps of space. London taxi drivers who must memorize thousands of streets and routes have been found to have larger hippocampi than average. The brain, in its infinite plasticity, grew more of the structure it needed. The thinking brain. Above all of these older structures spreads the cerebral cortex, the outer layer that makes us distinctly human. If you could unfold the cortex and lay it flat, it would be about the size of a large pizza, roughly 2 millimeters thick. But it's not flat. It's folded and convoluted, packed with deep grooves and ridges to fit more surface area into the skull. This crumpling is crucial. The cortex's power comes from its surface area. The more cortex you have, the more processing power. Evolution's solution was to fold it elaborately, like crumpling a piece of paper to fit it into a small box. The cortex is divided into 4 main lobes, each with its own primary functions, though they all work together in intricate ways. At the back sits the occipital lobe, home to the visual cortex. When light hits your retina, the signal travels through the optic nerve to the back of your brain. Here, in the occipital lobe, the raw data of light and dark, color and movement begins its transformation into vision. But here's something remarkable. You don't actually see with your eyes. You see with your brain. Your eyes are just cameras collecting light. The real magic, the creation of the rich, three-dimensional, meaningful visual experience you have right now, happens in your cortex. This is why damage to the occipital lobe can cause blindness, even when the eyes are perfectly healthy. And it's why people who lose their sight sometimes experience visual hallucinations. Their visual cortex, deprived of input, starts generating its own patterns. At the sides of the brain, at roughly ear level, sit the temporal lobes. These process sound in the auditory cortex.
interpret language in Wernicke's area, and house structures crucial for memory and emotion. The temporal lobes are where you recognize your mother's voice, where you understand the words being spoken to you, where you recall the melody of your favorite song. They're where you store knowledge about objects and their meanings, what a chair is, what blue looks like, who Mozart was. At the top and toward the back, we find the parietal lobes. These integrate sensory information from across the body, creating your sense of space and your body's position in it. When you reach for a cup without looking, knowing exactly where your hand is and where the cup is, that's your parietal lobe at work. When you feel texture or temperature or pain, the signal arrives first at the somatosensory cortex in the parietal lobe, mapping sensations onto a representation of your body. Interestingly, this body map is distorted. Your hands and lips, which have many sensory receptors, take up much more brain space than your back or legs. If you drew a person based on how much cortex is devoted to each body part, you'd get a grotesque figure with enormous hands and lips, what neuroscientists call a sensory homunculus. At the front of the brain, behind your forehead, spreads the frontal lobe, and particularly its foremost part, the prefrontal cortex. This is perhaps the most distinctly human part of the brain, the part that makes us capable of civilization, art, science, and philosophy. The prefrontal cortex is where executive function lives. Planning, decision-making, impulse control, working memory, attention. It's what allows you to hold information in mind while you work with it. It's what lets you resist immediate gratification for future rewards. It's what enables you to consider consequences before acting. Children have underdeveloped prefrontal cortexes, which is why they struggle with impulse control and planning. The prefrontal cortex is the last part of the brain to fully mature, not completing its development until the mid-20s. This is the part of the brain that makes you uniquely you. Your personality, your values, your sense of self, all of these emerge from the patterns of activity in your prefrontal cortex. We know this from tragic cases like that of Phineas Gage, a railroad worker in 1848 who survived an iron rod being driven through his frontal lobe in a blasting accident. Gage lived, but his personality changed dramatically. Once responsible and mild-mannered, he became impulsive, profane, unable to hold to plans or commitments. His friends said with heartbreaking simplicity, "Gage is no longer Gage." His structure of the brain had changed, and so the person himself had changed. The two hemispheres. Look at the brain from above, and you'll see that it's divided down the middle in two hemispheres, left and right, separated by a deep groove, but connected by a thick bundle of nerve fibers called the corpus callosum. For a long time, we thought these hemispheres were largely symmetrical, doing the same work on opposite sides of the body. But we've learned they have somewhat different specializations, though not as dramatically different as popular culture sometimes suggests. The left hemisphere, in most people, specializes in language, in logical and analytical thinking, in processing information. Let's return now to those neurotransmitters we discussed earlier, because understanding them is key to understanding not just how the brain works, but how it feels to be alive. Your brain is constantly bathing itself in chemicals, dozens of different neurotransmitters and neuromodulators, each affecting how neurons fire, how signals propagate, how you feel and think and perceive. Imagine for a moment that your consciousness is like music. The neurons firing are the individual notes, but neurotransmitters are like the tempo, the key, the emotional tone of that music. They determine whether your neural symphony feels urgent or peaceful, joyful or melancholy, focused or scattered. Let's explore some of the major players in this chemical orchestra. Dopamine, the molecule of motivation.
Dopamine is perhaps the most misunderstood neurotransmitter in popular culture. It's often called the pleasure molecule, but that's not quite right. Dopamine is more accurately the molecule of wanting, of motivation, of anticipation. It's what drives you to seek rewards, to pursue goals, to anticipate pleasure rather than experience it. When you're working towards something you want, your brain is releasing dopamine. When you're looking forward to a delicious meal, dopamine is flowing. When you check your phone, hoping for messages, that's dopamine too. Studies with rats have shown this beautifully. If you destroy the dopamine system in a rat's brain, it doesn't become unhappy, it becomes unmotivated. It will eat if food is placed in its mouth, but it won't cross the cage to get food even when starving. The wanting is gone, even though the liking remains. Dopamine is produced primarily in two small clusters of neurons deep in the midbrain, the substantia nigra and the ventral tegmental area. From there, dopamine neurons project to many brain regions, but especially to the striatum and the prefrontal cortex. This dopamine system is what learning hijacks. Every time you get a reward, especially an unexpected reward, dopamine neurons fire, strengthening the neural pathways that led to that reward. This is how habits form, how skills are learned, how addictions develop. Cocaine and amphetamines work by flooding the brain with dopamine, creating an artificial surge of motivation and anticipation. But the brain adapts, reducing its natural dopamine production and the sensitivity of dopamine receptors. Soon, nothing feels motivating anymore without the drug. This is addiction, a hijacked motivation system. Parkinson's disease, that cruel condition that robs people of smooth movement, is caused by the death of dopamine neurons in the substantia nigra. Without dopamine, the brain can't initiate and coordinate movements properly. Patients are given L-Dopa, a dopamine precursor, to replenish what's lost. Schizophrenia, conversely, may involve too much dopamine activity in certain brain regions, leading to hallucinations and delusions. Antipsychotic medications work by blocking dopamine receptors. One chemical affecting one neurotransmitter system can mean the difference between motivation and apathy, between coordinated movement and paralysis, between reality and psychosis. Serotonin, the mood stabilizer. If dopamine is about wanting, serotonin is about contentment, about being okay with what is, rather than constantly seeking what could be. Serotonin is produced by neurons in the raphe nuclei, clusters of cells along the brainstem. Like dopamine neurons, serotonin neurons project widely throughout the brain, affecting nearly every brain region. Low serotonin activity is associated with depression, anxiety, and obsessive-compulsive disorder. This is why many antidepressants, SSRIs like Prozac and Zoloft, work by blocking the reuptake of serotonin, leaving more of it available in the synapse. But serotonin does far more than just affect mood. It regulates sleep, appetite, body temperature, and pain perception. It plays a role in learning and memory. About 90% of your body's serotonin is actually in your gut, where it regulates digestion, which is why antidepressants often cause digestive side effects, and which is why your gut and your mood are so intimately connected. Serotonin is manufactured from tryptophan, an amino acid found in foods like turkey, eggs, and cheese. This is the scientific basis for the Thanksgiving turkey myth, that turkey makes you sleepy because it's high in tryptophan, which becomes serotonin, which makes you relaxed. The reality is more complex. Eating turkey in a typical meal doesn't actually raise brain serotonin levels significantly, but there's a grain of truth there. Certain psychedelic drugs, LSD and psilocybin, work primarily by activating serotonin receptors, particularly a subtype called 5-HT2A. This causes the profound alterations in perception and thought that characterize the psychedelic experience. Recent research suggests that these substances may have therapeutic potential for depression and anxiety, possibly by helping the brain break out of rigid patterns of thought.
GABA and glutamate, the yin and yang. GABA, gamma-aminobutyric acid, is the brain's main inhibitory neurotransmitter. Its job is to tell neurons to calm down, to stop firing, to be quiet. Without GABA, neural activity would run wild, each neuron exciting its neighbors in an escalating cascade. Epileptic seizures are in part a failure of GABAergic inhibition, neurons firing uncontrollably because the brake system isn't working. GABA creates a state of calm, reduces anxiety, promotes sleep. Benzodiazepines like Valium and Xanax work by enhancing GABA's effects, making neurons more responsive to this calming signal. Alcohol also enhances GABA activity, which is why it makes people feel relaxed and uninhibited. But too much GABA activity can be dangerous. At high doses, drugs that enhance GABA can cause unconsciousness or even stop breathing. And chronic use leads to tolerance. The brain compensates by reducing its GABA receptors so that when the drug is stopped, there's insufficient inhibition, potentially causing dangerous withdrawal seizures. Glutamate is GABA's opposite, the main excitatory neurotransmitter. Its job is to activate neurons, to get them firing. Glutamate is crucial for learning and memory. When you learn something new, glutamate strengthens the synapses involved through a process called long-term potentiation. This is the cellular basis of memory. Synapses that fire together, strengthened by glutamate, wire together. But too much glutamate activity is dangerous. In stroke or traumatic brain injury, damaged neurons release floods of glutamate, which overexcites nearby neurons, causing them to die in a process called excitotoxicity. The damage spreads like a wave from the initial injury site. GABA and glutamate work in balance, like two hands on the steering wheel of consciousness, one pressing forward, one pulling back, together creating controlled, purposeful neural activity rather than chaos. Acetylcholine, the attention molecule. Acetylcholine was the first neurotransmitter discovered, and it plays crucial roles throughout the brain and body. In the body, acetylcholine is what causes muscles to contract. When a nerve signal reaches a muscle, it releases acetylcholine, which binds to receptors on muscle cells, causing them to contract. Nerve gases and certain pesticides work by blocking the breakdown of acetylcholine, causing muscles to contract uncontrollably. In the brain, acetylcholine is crucial for attention, learning, and memory. It's released during states of focused attention, helping to sharpen sensory processing and strengthen memory encoding. Alzheimer's disease involves the death of acetylcholine-producing neurons. As these neurons die, patients lose the ability to form new memories and maintain attention. Early Alzheimer's treatments worked by preventing the breakdown of acetylcholine, trying to preserve what was still being produced. When you drink coffee, the caffeine blocks adenosine receptors. Adenosine normally suppresses acetylcholine release, so blocking it leads to increased acetylcholine activity. This is why coffee helps you focus and stay alert. Nicotine, the addictive compound in tobacco, directly stimulates acetylcholine receptors. This is why smokers often say cigarettes help them concentrate. Nicotine is temporarily boosting their acetylcholine system. Endorphins, the body's natural morphine, are neurotransmitters that are released during pain, stress, exercise, and other challenging experiences. They bind to the same receptors as morphine and heroin, dulling pain and creating a sense of well-being. This is the mechanism behind runner's high, the euphoric state that can occur during sustained aerobic exercise. After about 45 minutes of continuous running, endorphin levels rise, creating a natural high that makes the discomfort of exercise fade away. Endorphins may also explain the placebo effect. When people believe they're receiving pain medication, even if they're actually getting a sugar pill, their brains release endorphins, which actually do reduce pain. The expectation of relief triggers the brain's own pain control system. Acupuncture may work partly For most of the 20th century, neuroscientists believed that the adult brain was essentially fixed, that you were born with all the neurons you would ever have, and that after childhood development was complete, the brain structure was set in stone. This was the doctrine of the unchangeable brain. Children could learn easily, this thinking went, because their brains were still developing, still forming new connections. But adults? Adult brains were rigid, finished, unable to change in any fundamental way. This belief shaped everything: education, rehabilitation, our understanding of aging and brain injury. If the brain couldn't change, then damage was permanent. Learning had to happen early or not at all. The brain you had at 25 was more or less the brain you'd have at 75, just gradually wearing out. But this doctrine was wrong, profoundly, wonderfully wrong. The revolution began quietly, with scattered observations that didn't fit the model. In the 1960s, researchers studying lab animals found that rats raised in enriched environments, with toys, mazes, other rats to interact with, developed thicker cerebral cortices and more synaptic connections than rats raised in bare cages. The brain, it seemed, responded to experience by physically changing. In the 1990s, researchers studying London taxi drivers found those enlarged hippocampi we mentioned earlier. The brain region responsible for spatial navigation had actually grown in response to the demands of memorizing London's labyrinthine streets. Then came brain imaging studies showing that jugglers, after 3 months of practice, showed increased gray matter in brain areas responsible for visual motion processing. Musicians were found to have enhanced auditory cortex and motor cortex in regions controlling their instrument. The evidence mounted until it could no longer be ignored. The adult brain was not fixed. It was plastic, capable of reorganizing itself, forming new connections, even growing new neurons in certain regions. We call this neuroplasticity, and it has revolutionized our understanding of the brain. The mechanisms of plasticity. Neuroplasticity occurs at multiple scales, from molecular changes at individual synapses to large-scale reorganization of brain regions. At the smallest scale is synaptic plasticity, the strengthening or weakening of connections between neurons based on their activity. Remember that phrase, neurons that fire together, wire together. This is called Hebbian learning, after neuroscientist Donald Hebb, who first proposed it. When two neurons are repeatedly active at the same time, the synapse connecting them strengthens. The more often they fire together, the stronger the connection becomes. This is the physical basis of learning and memory. Every time you practice a skill, every time you recall a fact, you're strengthening specific synaptic connections. The opposite also happens. Neurons that fire apart wire apart. Synapses that aren't used weaken and eventually disappear. This is synaptic pruning, and it's crucial for efficient brain function. Your brain doesn't just add connections, it also removes them, eliminating weak or unused pathways to focus resources on the connections that matter. This is why use it or lose it is literally true for the brain. Skills you don't practice fade because the synaptic connections supporting them weaken. Languages you don't speak become harder to recall. Memories you don't revisit grow dim. At a larger scale is structural plasticity, actual physical changes in brain tissue. This includes the growth of new dendritic spines, the tiny protrusions where synapses form, the extension of axons to form new connections, changes in the myelin sheathing that insulate axons, the growth or shrinkage of brain regions, even in certain brain areas, the birth of entirely new neurons. Neurogenesis, new neurons in the adult brain. For decades, it was dogma that adult brains couldn't generate new neurons. You were born with all your neurons, and from there it was all downhill. Inevitable loss, no replacement. But in the 1990s, this dogma fell. Researchers discovered that the adult human brain does produce new neurons, a process called neurogenesis, in at least two regions, the hippocampus and the olfactory bulb. In the hippocampus, thousands of new neurons are born every day, migrate to their positions, extend their axons and dendrites, and integrate into existing circuits. These new neurons seem to be particularly important for forming new memories and for pattern separation.
the ability to distinguish similar experiences from each other. What affects neurogenesis? Almost everything. Exercise increases it. Studies in rodents and humans show that aerobic exercise, running, swimming, cycling, significantly boosts the birth of new hippocampal neurons. This may be one mechanism by which exercise improves memory and protects against cognitive decline. Stress decreases it. Chronic stress, through the sustained release of stress hormones like cortisol, suppresses neurogenesis. This may be part of why chronic stress is associated with depression and memory problems. Learning itself increases neurogenesis. Challenging your brain with new skills and information appears to encourage the birth of new neurons. Antidepressants increase it. Many antidepressants boost hippocampal neurogenesis, and this effect may be part of how they work. Depression suppresses neurogenesis. Antidepressants restore it. Sleep affects it. Deep sleep seems to be important for the survival of newly born neurons. The discovery of adult neurogenesis fundamentally changed how we think about brain health and aging. The brain isn't a slowly dying organ, inevitably losing neurons with no replacement. It's a dynamic organ, capable of renewal, if we provide the right conditions. The brain after injury. Perhaps the most dramatic demonstrations of neuroplasticity come from studies of brain injury and stroke. When part of the brain is damaged by stroke, trauma, or surgery, neighboring regions can sometimes take over the lost functions. The brain reorganizes, rewiring itself to compensate for the damage. Consider stroke patients who lose the ability to move one arm, with intensive rehabilitation, forcing themselves to use the affected arm repeatedly despite difficulty. Many patients recover function. Brain imaging shows that adjacent brain regions, or even the corresponding region in the opposite hemisphere, begin to control the affected arm. The brain has found a workaround, a new pathway to accomplish what the damaged pathway can no longer do. This doesn't always work. Severe damage can be too great to compensate for, but the potential for recovery is far greater than we once believed. There's a therapy called constraint-induced movement therapy, developed by Edward Taub, which has stroke patients with arm paralysis forced to use their affected arm by constraining the good arm. Unable to rely on their healthy limb, they must use the damaged one. The brain responds to this forced practice by reorganizing, gradually restoring function that doctors once thought permanently lost. Similar principles apply to other types of brain injury. People who lose their vision experience expansion of their auditory and tactile cortex. The brain reallocates resources from the unused visual system to other senses. Blind people who learn Braille show massive expansion of the cortical representation of their reading finger. The brain is pragmatic. It uses what it needs and repurposes what it doesn't. Critical periods and sensitive periods. Neuroplasticity is greatest during childhood. There are critical periods, windows of time when the brain is especially sensitive to certain kinds of experience. For language, this critical period extends from infancy through early adolescence. Children can learn multiple languages effortlessly with native-like pronunciation and grammar if exposed during this window. After puberty, language learning becomes much harder. You can still learn new languages, neuroplasticity doesn't shut off, but you'll likely have an accent and grammar will require conscious effort rather than feeling intuitive. For vision, the critical period is even earlier. If a child is born with cataracts that aren't removed or has a misaligned eye that isn't corrected in the first few years of life, the visual system may never develop normally, even if the physical eye problem is later fixed. The brain needs visual input during this critical period to wire itself correctly. Why do critical periods exist? It's a trade-off. Young brains are maximally plastic, able to adapt to whatever environment they find themselves in. But this flexibility comes at a cost: instability, vulnerability to disruption. As the brain matures, it trades flexibility for efficiency and stability. Circuits become more fixed, locked in place by molecular brakes on plasticity. This makes the adult brain more resistant to change, but also more stable, less likely to be knocked off course by random noise. Recent research is exploring whether we can reopen critical periods in adulthood, essentially making the adult brain young again, temporarily, to facilitate learning or recovery. Early results in animals are promising,
suggesting this may someday be possible. Oxytocin, the bond builder. Oxytocin is sometimes called the love hormone or the cuddle chemical. And while these names are oversimplified, they capture something real. Oxytocin is released during childbirth, helping trigger contractions. It's released during breastfeeding, promoting bonding between mother and infant. It's released during orgasm, creating feelings of closeness and attachment between partners. More broadly, oxytocin seems to facilitate social bonding and trust. Studies have shown that giving people oxytocin via nasal spray makes them more trusting in economic games, more empathetic to others' emotions, and better at reading facial expressions. Prairie voles, small rodents that form lifelong pair bonds, have high levels of oxytocin receptors in their reward centers. When these voles mate, oxytocin release bonds them to their partner. Meadow voles, a closely related species that doesn't form pair bonds, has far fewer oxytocin receptors. The difference in social behavior comes down, at least partly, to this one chemical system. But oxytocin isn't just about universal love. It also promotes in-group bonding at the expense of out-groups. People given oxytocin become more trusting and cooperative with people they perceive as similar to themselves, but may become more defensive or hostile toward outsiders. Oxytocin, it seems, doesn't make us love everyone. It makes us love our own people more strongly, for better and worse. The endocannabinoid system. One of the more recent discoveries in neuroscience is the endocannabinoid system, a network of receptors and signaling molecules throughout the brain and body. Endocannabinoids are molecules naturally produced by the body. They got their name because they're similar to cannabinoids found in marijuana. In fact, marijuana works by activating this natural system. Endocannabinoids play roles in appetite, pain sensation, mood, memory, and stress response. They seem to act as a brake on other neurotransmitter systems, fine-tuning neural activity. This is why marijuana affects so many different things: appetite, the munchies, pain perception, mood, memory. It's activating a system that normally regulates all of these functions. The endocannabinoid system may also explain why exercise improves mood. Recent research suggests that runner's high isn't just endorphins, it's also endocannabinoids released during prolonged exercise, binding to cannabinoid receptors in the brain. The neurochemical self. What's remarkable about all of these neurotransmitters is how profoundly they shape your subjective experience, while you remain largely unaware of them. Right now, as you listen to these words, your dopamine system is modulating your motivation and attention. Your serotonin system is influencing your mood. GABA and glutamate are maintaining the balance of activity in your cortex. Acetylcholine is sharpening your focus. Tiny changes in these chemical levels, so small you couldn't detect them with any conscious awareness, can mean the difference between feeling alert or drowsy, calm or anxious, motivated or listless. When someone develops depression, it's not just a psychological state, it's a physical change in brain chemistry. When trauma causes PTSD, it alters the stress response systems in the brain. When someone falls in love, it's not just metaphor to say their brain chemistry has changed. It literally has, with surges of dopamine and oxytocin creating the obsessive thoughts and euphoric feelings of new romance. You are, in a very real sense, the sum of your neurochemistry. Change the chemistry, and you change the person. This can be frightening. It seems to reduce human experience to mere molecules, to suggest we're nothing but chemical reactions. But it can also be liberating. Depression isn't a moral failing or a lack of willpower. It's a medical condition rooted in brain chemistry. It can be treated, just as diabetes or high blood pressure can be treated. We are chemical beings, but the symphony that arises from all these chemicals interacting, that is somehow greater than the sum of its parts. Similar principles apply to other types of brain injury. People who lose their vision experience expansion of their auditory and tactile cortex. The brain reallocates resources from the unused visual system to other senses. Blind people who learn Braille show massive expansion of the cortical representation of their reading finger. The brain is pragmatic. It uses what it needs and repurposes what it doesn't. Critical periods and sensitive periods. Neuroplasticity is greatest during childhood. There are critical periods, windows of time when the brain is especially sensitive to certain kinds of experience. For language, this critical period extends from infancy through early adolescence. Children can learn multiple languages effortlessly with native-like pronunciation and grammar if exposed during this window. After puberty, language learning becomes much harder. You can still learn new languages, neuroplasticity doesn't shut off, but you'll likely have an accent and grammar will require conscious effort rather than feeling intuitive. For vision, the critical period is even earlier. If a child is born with cataracts that aren't removed or has a misaligned eye that isn't corrected in the first few years of life, the visual system may never develop normally, even if the physical eye problem is later fixed. The brain needs visual input during this critical period to wire itself correctly. Why do critical periods exist? It's a trade-off. Young brains are maximally plastic, able to adapt to whatever environment they find themselves in. But this flexibility comes at a cost: instability, vulnerability to disruption. As the brain matures, it trades flexibility for efficiency and stability. Circuits become more fixed, locked in place by molecular brakes on plasticity. This makes the adult brain more resistant to change, but also more stable, less likely to be knocked off course by random noise. Recent research is exploring whether we can reopen critical periods in adulthood, essentially making the adult brain young again temporarily to facilitate learning or recovery. Early results in animals are promising, suggesting this may someday be possible. The learning brain. Every skill you've ever mastered, from walking to reading to driving a car, represents physical changes in your brain. When you first learn something, it requires intense conscious effort and engages broad swaths of cortex. Watch a child learning to tie their shoes, tongue sticking out in concentration, eyes focused, whole body tense with effort. Their prefrontal cortex is working overtime, consciously directing every movement. But with practice, something remarkable happens. The skill becomes automatic, moving from cortex to basal ganglia and cerebellum, from conscious control to automatic execution. The brain becomes more efficient, using less energy to accomplish the same task. Brain imaging studies show this beautifully. When someone first learns to play a piano piece, huge areas of their brain light up. After weeks of practice, only small, focused regions remain active. The brain has optimized the circuit, trimming away unnecessary activity. This is why practiced skills feel effortless. Your brain has literally rewired itself, creating efficient neural pathways that perform the skill automatically, without conscious thought. This is also why breaking bad habits is so hard. That habit, whether it's biting your nails, checking your phone constantly, or reaching for unhealthy food, has carved its own neural pathway. Changing the behavior means weakening that pathway while building a new one, fighting against neural connections that have been strengthened through repetition. But it can be done. The brain's plasticity works both ways. Just as practice strengthens pathways, the lack of practice weakens them. Replace an old habit with a new one, and eventually the new pathway will become the default. The musical brain. Musicians provide some of the clearest examples of experience-driven neuroplasticity. String players have enlarged cortical representations of their left-hand fingers, the fingers that press the strings. The more years they've played, the larger this representation. The brain has devoted more cortical real estate to the fingers that need the finest control. Pianists show enhanced connections between auditory and motor cortex. Hearing a note automatically activates the motor program to play that note. They've trained their brain to link sound and movement so tightly that they become almost inseparable. Musicians who started training before age 7 show structural differences in the corpus callosum, the bridge connecting the brain's hemispheres, suggesting that early musical training enhances communication between hemispheres. Drummers who must coordinate independent rhythms in each limb show enhanced connectivity in brain regions responsible for motor coordination. These aren't just correlations.
Training studies show that even in adults, musical training causes measurable brain changes within months. The musical brain is a plastic brain, physically shaped by years of practice. The bilingual advantage. Speaking multiple languages also leaves its mark on brain structure and function. Bilinguals show enhanced executive function, better attention control, task switching, and working memory. They're constantly managing two languages, deciding which to use, suppressing one while using the other. This constant mental exercise seems to strengthen the prefrontal networks responsible for cognitive control. Brain imaging shows that bilinguals recruit additional frontal and parietal regions when processing language, compared to monolinguals. They've built extra neural machinery to handle the demands of managing multiple languages.